Hello, this is Mrs. Brown, and today we're going to talk about square root functions. And so the first question is, what is a square root function? Well, basically, it's just a function that contains the square root of a variable. And here's the example of the parent function. So f of x equals the square root of x. That would be a square root function. The other vocabulary word that you need to know for today is the radicand. This is the expression under the radical sign, and it has to come out positive for real numbers. So we're not talking about imaginary numbers right now. So we're going to exclude any x values that would make this negative when we write our domain. Okay, and so that means that our domain will change depending on the situation when we start translating and looking at that. Okay. So here's the parent function. F of x equals the square root of x. The domain is x is greater than or equal to 0, and the range is y is greater than or equal to 0. So we got everything's positive right here. As you look, it's a nice little curve. You can kind of imagine it's almost like half of a parabola that's laying down on its side. You've got that nice little kind of starts out slower and then gets into this nice big curve. And so again, and I just have my values, but this is the parent function. And so we're going to look at what happens when we dilate, reflect, translate this parent function, what it does to the graph. Okay. So the first thing is to look at the formula. What's what and what's going to do what. Okay. So the number that's multiplied in front of the radical sign is going to be the dilation. So it's either going to stretch it if the absolute value is greater than 1. So if it's like, say, 3 or -3, it's going to stretch it vertically. It's going to compress it if it's between 0 and 1. So if it's like a half or -1/3, it's going to compress the graph. Okay. The other thing is, if it's negative, it actually reflects it over the x-axis. So this can also be a reflection. If it's negative, that reflects it over the x-axis. Okay, and we'll look at an example of that in a minute. K is a vertical translation. If it's greater than 0, you go up. If it's less than 0, you go down. Notice it is not under the square root sign. Okay, the vertical translation is not part of the square root sign, it's after it. So you take the square root first and then change up or down. The H, however, is the horizontal translation, and you notice that's under the radical sign. So it's under that square root sign. It's part of the radicand. So that's really important because you're adding or subtracting that before you take the square root. And so if x is greater than 0, it moves to the left, and if h is greater than or less than 0, it moves to the right. And I think I just said x is h. Okay. All right, so let's look at some examples of dilation. And so what I did is I wanted to contrast a couple of different types of each one so that you can kind of see what's going on. So this is a +2 and a -2. So in other words, both of them are stretches because this number, the absolute value, is greater than 1, but one is positive and one is negative. So one is actually reflecting over the x-axis. Okay, so if you look, the domain and the range actually haven't changed at all when A is positive. That's not affecting that. I've substituted in my values, and you can just see that this looks taller than the parent function, which was a more gradual kind of curve, or a smaller curve as you look at this. So this is stretched it vertically, okay? If you look at this one, notice that your range has changed. What has changed is the direction of that sign. So instead of being greater than or equal to, it's less than or equal to. So your range, you notice, is just a reflection. It's the mirror image. If we put those two together, we get almost like a parabola shape. And so this would be the same thing, but reflected down. Okay? So keep that in mind. It's really important understand these parts when you're graphing and you start to graph it and you see that you have a positive or a negative A. That kind of tells you a lot about where the graph's going to be. And so that gives you a good idea and helps you spot check if you make mistakes. All right, so let's look at a vertical translation. So vertical is with K, so I've got a -2 and I've got a +2. Again, looking at the difference between those. So you notice that with a vertical translation, my domain hasn't changed at all, but my range did. So for a -2, notice that my y value when x is 0 is -2, and my range changed to reflect that. And then over here, you notice that when x is 0, y is 2. So again, my range changed to reflect that vertical translation, okay? So the -2, we'll move it down 2 spaces. So you can see it's basically the same graph down 2. This is up 2, so compared to the parent function, it's the same shape. It's just moved vertically, okay? And again, when you're evaluating this, the k part is outside of the square root. So you take the square root and then subtract 2. So for instance, if I take 4, the square root of 4 is 2, minus 2 is 0. And that's where that comes from, okay? So again, vertical translations, it's outside of the radical sign, so it's outside of the square root, and it moves the graph up or down depending on whether it's positive or negative. Okay. All right, so let's take a look at a horizontal translation. Again, notice that my square root sign goes over the plus, so it's part of it. It's grouped underneath, which means it has to happen before you take the square root. And so I've done a +2 and a -2. So when you add 2 under the radical sign, it moves to the left. Okay, so if we look at that, let's say I start with -2. -2 for x plus 2 is 0. And so again, it moved my point from 0, 0 for the parent function to the left 2 spaces. If you look over here, remember that we said that you would have to exclude x values that made the radicand, so this part under the square root sign, negative. So notice I don't start with x equals 0, because if I did, 0 minus 2 would be -2, and I wouldn't be able to take the square root and get a real number. So therefore, I moved my domain to start with 2, because that's going to make it positive under the square root sign. So the radicand will be positive if I start with 2. So again, I excluded the values that would have made the radicand negative. Okay, so -2 moved it to the right, +2 moved it to the left. Okay, that's not exactly intuitive sometimes when you're kind of thinking about it. So this is where it's really important a lot of times to kind of put a couple of points in and see what happens, because it's really easy to mix up the horizontal translation. If you're going to make a mistake, it's probably going to be on this step. Okay. All right. So now that we've looked at dilations and translations, let's look at an example. Okay. So looking here, I've got a couple of things that are happening. I've got an A value. That means I have a dilation. In this case, since it's a half, that means it's a compression instead of a stretch. I have a negative A, which means it reflected it over the x-axis, and I don't have any horizontal translation because there's nothing under the square root sign with the x. However, there is a vertical translation. So actually, if I were describing what's happening with this graph, I would have to describe 3 things compared to the parent function. It's a dilation, which is compressed by a factor of 1/2. You have a reflection over the x-axis. And you have a translation, specifically a vertical translation of 1 unit down, because it's a -1. So 3 things are actually happening with this graph, okay? So let's go ahead and substitute in. If I put in 0, this whole term is going to be 0, so I'm left with -1. So the square root of 1 is 1 times -1/2 is -1/2. -1 would be -1.5, so -1.5, however you want to say that. Okay, the square root of 4 is 2. And -1/2 times 2 would be -1. -1 is -2. Square root of 9 is 3. So when you take a half, that'd be -1.5. So this would be 2.5. Okay, so again, I can get those values substituting it in. Notice I picked perfect squares. I don't have to do that. It does make it easier sometimes when you're graphing. But if you don't pick perfect squares, that's okay. You're using a calculator, just kind of round to like the tens place to get an approximate spot, and that will be just fine. Okay, we actually did that on the horizontal translations for one of the points. But you don't have to do that unless you feel comfortable. It's kind of like whichever seems to work for a particular question. Okay, so for this one, I just use perfect squares. If I'm looking at the domain, okay, my domain, I didn't have a horizontal translation, so my domain is the same. Okay, now my range is definitely different from the parent function. I've reflected it, so that means my sign is going to go this way instead. Okay, remember that flips the sign when I reflect it. And I had a vertical translation, so it's going to be less than or equal to -1. So again, as you're looking at your information, you have to figure out, did you have a change in domain? Did you have a change in range? The change in domain is going to come from your horizontal translations, because remember, the domain is the horizontal axis. This is coming from both reflections, because you're reflecting over the x-axis, and from the vertical translations. All right, so if we were going to draw an approximate graph of this, I probably need further down here. So 0, -1, and then I have 1, -1.5, and I have 4, -2, and I have 9, so 5, 6, 7, 8, 9 at -2.5. So this graph would look something like this. Okay. I hope this helps, and have a fabulous day.